Now let us start a new lecture, which will be devoted to some basic methods of manifold learning. So the whole idea of manifold learning is that we can model the structure of the data in unsupervised way, as assuming that the data is located in the vicinity of a manifold which is embedded into multidimensional space. So I will, in this part of the lecture, I will try to precise what does it mean exactly. And the first thing that we have to understand is what does it mean manifold, and what people assume by the notion of manifold when they perform unsupervised learning. So strictly speaking, in the mathematical sense, m-dimensional manifold is a topological space with the property that each point has a neighborhood that is homeomorphic to the Euclidean space of dimension m. Simply speaking, it means that if you take a point on a manifold and consider a local neighborhood, so some points of the manifold which are close to the selected point, then locally at small scale, everything will look like an m-dimensional Euclidean space, which means that you have a Euclidean matrix. So this is a strict mathematical definition of manifold. So manifold, m-dimensional manifold can be embedded into a space of larger dimension, P, where P is bigger than M. And a simple example of such embedment is here, where in the three-dimensional space, so P equal to 3, you have data points which are located close to a manifold of dimension 2. So if you take any point in this distribution and you consider some kind of very small vicinity neighborhood of this point, you will see that they really look like a uniform sample from a two-dimensional plane. So this is why this configuration of points satisfies the assumption of this manifold hypothesis, that the data points are located close to a low-dimensional manifold. So when we talk about manifolds, we have to distinguish the notion of geometry and topology, even though sometimes these two things are mixed up in scientific articles or in description of methods. So strictly speaking, the geometry is let's say position of points they defined by the position of points of the manifold in the m-dimensional space, and the geometry is defined by the global matrix, which is again, strictly speaking, in mathematical terms, is described by so-called Riemannian differential geometry. We are not going into details of these descriptions, which should be subject of another course in mathematics. But what I would like to say here is that we should distinguish geometry and topology. So geometry for us will be the exact, let's say, shape of the manifold, I mean, how it's embedded in the multidimensional space, and topology is a more generic characteristics of the manifold. So by topology, usually we define some kind of global characteristics. For example, we can distinguish, in this case, the manifold is topologically equivalent to a plane, while we might have manifolds of different topology. For example, we might have a manifold which will be topologically equivalent to a sphere, or to a torus, or some other different topologies. So the manifold, strictly speaking, doesn't have to be connected or have to be closed like here. The manifold might be infinite, or might consist of several parts. And something which is tightly related to the notion of geometry of the manifold is the notion of geodesic distance. So the idea is that if we take 2 points on the manifold and we would like to connect them somehow by a shortest path from point A to point B, and since we are allowed to go only through the points of the manifold and not directly from point A to B in the ambient space, then we have, our geodesic distance might be much larger than the direct distance computed in the ambient multidimensional space. So it's an illustration here. So to go from point A on the manifold to the point B here, you have to cross across the whole this path. So to pass through the manifold. And so the point is that if we know the geometry of the manifold, then we can compute this geodesic distance, which is simply a shortest path along without exiting from the manifold. So in manifold learning, we talk about several types of manifolds, which are widely used. So one type of the manifold is a so-called principal manifold. The idea is it's called principal manifold because there is this idea of data approximation. So principal manifold is such a manifold which approximates the data, usually in the sense of minimizing mean square distance. So, but quite informally, usually this definition of principal manifold is done quite informally. So it says that in m-dimensional principal manifold, which passes through the middle of the data point cloud. Through the middle, it means that it tries to minimize the distance to the data points. So we will make this notion more precise, but one simple example of a principal manifold is constructed just by PCA, as we already discussed. So let's say PCA can be defined as a linear manifold approximating the data in the sense of least squares. So in this sense, principal component analysis constructs the simplest principal manifold, which is linear principal manifold. Other methods of matrix factorization, such as ICA and MF, they also define manifolds which are not necessary, but these manifolds are not necessarily principal. Or at least, it's discussable what kind of manifolds. At least what can be said that any matrix factorization technique will define a linear manifold. When we talk about, let's say, manifold as a data model, usually in all these manifold learning techniques, we assume that the points are uniformly sampled from the manifold. And this is a kind of the most fundamental assumption and the most violated assumption in the case of real life data. Of course, the data are not uniformly sampled from the manifold, but in some cases we can pretend that this is the case and act as if it would be true. Some methods, and here we come to quite important point, because we will have part of the lecture devoted to one type of methods and another lecture devoted to another type of methods. And here, once again, we have to distinguish projective methods and injective methods. And once again, I remind you that in the projective methods, we learn only projections. And in the case of manifold learning, we learn projections on the manifolds, but these manifolds exist only in our imagination. We don't have an explicit formula for this or explicit representation of these manifolds. In other cases, we learn the manifold geometry or topology, or even topology, explicitly. So we can, after we applied the injective method, we can in principle get rid of the data, and what we will be left with is the geometry and the topology of the resulting manifold, which we can use even without the data, or we can use it to generate new data which would be located close to the same manifold. And the last remark, I mean, we talk about manifold learning, but frequently what people learn, what a method learns is not strictly a manifold. I mean, there are some kind of special points, or there might be points on these things that are frequently called manifolds, which are locally not homeomorphic to Euclidean space. So let's say the notion of manifold, which is used in the manifold learning, is a loose notion, I mean, with respect to the formal mathematical definition. This is something which is important to have in mind. Moreover, I mean, we talk about manifold learning, but frequently, I mean, even if you type in Wikipedia manifold learning, you will be redirected to a page with the title Nonlinear Dimensionality Reduction. And indeed, frequently, when people mention manifold learning, for example, if you go to scikit-learn standard library, the methods of manifold learning which are implemented here, and strictly speaking, we don't learn the manifold explicitly. What we do is nonlinear dimensionality reduction. So in many cases, these two things are synonymous. Just, I mean, connected to the previous lecture. In the previous lecture, we learned about mostly about linear dimensionality reduction methods. So instead of saying that in this lecture we will be studying manifold learning, we could say that in this lecture we study nonlinear dimensionality reduction, and it will be also correct. The main role of manifold learning in unsupervised machine learning is visualization of data, but not only. I mean. For this reason, the manifolds that we extract from the data are frequently two-dimensional manifolds or three-dimensional manifolds. And then by projecting points onto these really low-dimensional manifolds, we can visualize the structure of the data in 2D or 3D space. Also, kind of important remark that frequently the manifold learning techniques are applied after linear dimensionality reduction. So in many cases, before application of nonlinear manifold learning, you reduce the dimensionality by linear approaches, such as principal component analysis, or it might be some other linear methods. In many situations, first of all, it reduces your computational cost of your calculations. And second, in many cases, it gives more stable results because you get rid of some of the effects connected to high-dimensional geometries, which are increasingly difficult to treat in higher dimensional space when we talk about manifold learning. So one of the basic tools for the methods of manifold learning is the use of KNN or Epsilon graphs. So these are two basic types of neighborhood graphs. The notion of K nearest neighbor graph, KNN, we already discussed in the first lecture. So Epsilon graph is another type of neighborhood graph where instead of connecting a point to just K nearest neighbors, you connect a data point to other data points which are located not further away than a certain radius epsilon. So this is the kind of the definition of a simple epsilon proximity graph. We will see how this definition is modified in different methods. And frequently, people already say that KNN graph or Epsilon graph is a manifold, which is totally incorrect, because KNN graph by any means locally remains the structure homeomorphic to the structure of Euclidean space. So it would be incorrect to call a KNN graph or Epsilon graph a manifold. But the manifold can be somehow, let us say, distilled from the structure of KNN graph or Epsilon graph. In particular, KNN graph might help to define the geodesic distance, or to approximate the geodesic distance on the manifold, and this might help to recover the manifold structure in the data. So then, as frequent word which is used when we read about manifold learning is the word embedding. And once again, people use this word in several different meanings. Well, again, general mathematical definition of embedding is embedding, or sometimes it's called embedding, is a situation when some mathematical structure is contained within another mathematical structure. So in the pictures that I showed in the beginning, so we have one mathematical structure is p-dimensional Euclidean space, and then we have a structure of the manifold which is kind of contained in this p-dimensional space, but the nature of this manifold, its intrinsic dimension is m, so m-dimensional. So in this case, we say that M manifold is embedded in p-dimensional space. Frequently, when people talk about nonlinear dimensionality reduction methods, the result of the projections, of finding the projections in low-dimensional space, sometimes they are called low-dimensional embedding. So this is a frequently used wording. Also, when people talk about embedded space, they also frequently mean this latent space, or low-dimensional latent space. So in the space of dimension m. The word embedment is also embedding. It's also used in another context, in the context of graph embedment. It's a set of approach which looks to position a graph nodes. So I mean the input for these methods is a structure of a graph, maybe with some information attached to the node label to the nodes. And the graph embedment approach looks to position the nodes of the graph in some abstract high-dimensional space, such that afterwards you will be able to apply these methods of machine learning. For example, non-negative matrix factorization for this configuration of nodes. And this embedment depends on many things. In particular, it depends on the structure of the graph. So, for example, you can take a graph of social network and embed it in some high-dimensional space. We are not going to talk about these methods, but the word embedment is sometimes used in this context as well. So, what you will learn in this lecture. So, once again, it's important for you to be able to distinguish between projective and injective methods of manifold learning, because depending on this, you will be able to perform particular tasks of unsupervised learning. So, for example, using projective methods, it's much more difficult to create so-called generative data models. While with injective methods, usually it's much simpler. You can do it directly. You will have an idea of principal manifolds and how these principal manifolds, nonlinear principal manifolds, are constructed. This can be considered as a nonlinear extension of PCA. And we will see some generalization of principal manifolds to graphs, for example, to principal graphs. I will devote a part of the lecture on two most popular methods for nonlinear dimensionality reduction, which are used today. So one is called TSNE, another is called UMAP, and both of them are kind of part of the standard toolbox for dimensionality reduction. I'm pretty sure that most of you already use them, but we are going to talk about how they build these methods. And in the last part of the lecture, we'll talk about the principles. I'm not going to go into the details of this field because, once again, our course is not about neural networks. It's about more fundamental kind of and basic methods of machine learning. But when we talk about manifold learning, I think it's important to mention the idea of autoencoder or variational autoencoder for this purpose of manifold learning. because these kind of methods become extremely popular these days. So here I finish with my introduction and switch to the next part of the lecture.